All right, let's jump into week 2 measurement foundations, starting with our measurement types. So we talked last week about base units and that they're the labels given to different types of measurements. So now we're just going to define these different types of measurements with a single word. So for each one, we're going to define what does it measure. Time is a measure of duration. From the time of start to finish of an event, the duration, and again, remember we measure that in seconds. Length is a measure of distance between 2 points, measured in meters. Mass is a measure of the matter in a sample, how much stuff there actually is, how many particles are present. Temperature is actually a measure of the movement of particles in a sample. Or sometimes it's also referred to as the heat. The more heat, the more the particles are bumping into each other and moving faster and faster. The less heat, the slower they're moving. And that's measured in degrees Celsius, or we talked about capital K is in the Kelvin scale. Kelvin scale is based on absolute zero. So at 0 Kelvin, there is absolutely no movement of particles. And we've actually not been able to reach absolute 0 Kelvin in the field of science. They've gotten really close to it. It's just really hard to observe 0 Kelvin because simply by observing it, you're adding energy to the system. So all of that to say, temperature is the movement of particles. That's what we're actually measuring. And lastly, volume is the amount of space that something takes up, and we measure that in liters. So those are kind of our one-word definitions for the different measurement types. We're going to actually split these notes into two parts. So the first part, we're going to talk about estimation and significant figures, and then I'll make another part 2 video where we'll talk about scientific notation. So let's jump into estimation. And when we're dealing with measurement of any type, we want to give a proper reading for whatever glassware we are reporting from. Some equipment is better than others to give a value because it has more specificity, more tick marks that give us a better reading. So we have to consider that and include that with our estimation. So whenever we're making an estimation, we need to be reading a measuring tool with the appropriate amount of certainty. And when we report that, we have to include what we know for sure, and then we can only make one estimation. One value can be estimated. No more than that. So I'm going to talk you through what that means. We can only estimate one value. Okay, we have some examples down here on example 1 for finding measurement. Sometimes things are given to us digitally and we don't have to estimate at all. Other times they're in equipment and that's where we have to make our estimation. So of course this digital balance here, I'm just going to do this first part, record the measurement and estimate the value. A balance, remember we talked about last week, a digital balance, that's going to be giving us mass, probably in grams. And because this is digital, we do not need to estimate anything. It's already done for us. We will finish significant figures in a moment. First, we're just going to do the estimations. So let's look at our first actual estimation with our graduated cylinder here. And as you can see, the liquid goes in between some tick marks that we know. So it looks like each tick mark is a tenth, when it's definitely between 1 and 2. We do not have to estimate the tenths place either because we have these tenths place markings. 10, 20, 30, 40, 50, 60, 70. Okay, it's between 0.6 and 0.7. You see that? So our numbers that we know for sure are 1's place. Definitely 1 point something, and it's definitely 10th place is 0.6 We definitely, for sure, know those values based on tick marks. Now we need to make one estimate value, like we said up here in our notes section, estimate one value. So our value estimated here will actually be the hundredths place, and we'll estimate between this 0.6 and 0.7. I'm going to estimate that this is about a little over halfway between the two, so 1.66 milliliters. That's going to be my estimate for the proper amount of certainty that we have. We provide one estimated value and all of the ones we know for sure. Let's do this length value. Oh, I forgot to tell us the measurement type. This is volume. Okay. The next one we said is length. Okay. So we know for sure it's between 3 and 4, so we can write 3. And now we're going to make an estimate because we don't know with certainty anything else. So our area of estimation here is between the 3 and the 4. I'd say that's about 0.2. Now the beauty of the estimation is maybe you thought it was 0.3 or you thought it was 0.1. You can report that honestly, because when we are communicating our number here, it's saying this is the number, the last one is the one that I don't actually know for sure. That's why this system works, because all scientists do this. They know that the last value has some error in it, because no measuring device is going to be able to be perfectly correct or perfectly perfect in its measurement. There has to be error in it. The stopwatch, again, it's a digital measurement, so this we can write time for our stopwatch, just 37 seconds. When you're dealing with things that are digital measurements, there's still error that is already taken into account. So our seconds, they already are telling us that the ones place is our area of uncertainty, and with the digital mass scale, they're telling us the hundredths place is our area of uncertainty. Okay, continuing on here, this looks like a thermometer, so that is temperature. And let's go ahead and record all of our known values. It's definitely 91.5 something because we're in between 0.5 and 0.6. So our one estimated value now is going to be based off of our actual line of the liquid. So I'm going to estimate that's about 91.57 degrees Celsius. That's what I'm estimating. So my hundredths place is the estimated value. All the rest I know for sure. And lastly, this beaker. This is measuring volume. We know for sure it's in the 40s. And now we get to estimate. I'm going to say 48 milliliters. Always estimating just one value and reporting everything else you know for sure leading up to that. Now let's take a look at significant figures. When we are recording an estimate, all of the numbers that we know for sure and the numbers that are based off of an estimate are considered significant. It doesn't mean that any number that is insignificant isn't important or can be dropped. It just means it's not part of the actual estimation. For example, it might be a placeholder. Maybe it's holding, the hundredths place. If you have 500, those zeros at the end are simply holding a place. So let's talk a little bit about significant figures. These are numbers that are significant to the estimated value of the measurement, or estimation of a measurement. So some numbers that are always part of that estimation, let's just make a little list here. That's always going to include non-zero numbers. They're always going to be part of our estimation based on either tick marks or making that one estimate. Anytime we have zeros, that are between non-zero numbers, I'm going to call that sandwiched zeros. Like if you had 101, that zero would be sandwiched. It's part of our estimate. Other things that are significant are final zeros after a decimal. Just like our digital scale there, 65.00, both of those zeros would be considered part of the estimate. They're after the decimal. Now, things that are not included, I kind of said this earlier, placeholder zeros are not part of our estimate. They're just holding a place. Some examples of that, like I said, 500 or 0.001, just holding those place values. They're not actually part of the estimation, so they're not significant to the estimation. Like 500, those zeros are not, those zeros not. They're just holding a place, okay? So let's go back to our examples here. We're going to talk about significant figures for these, and then I'm going to stop this and we'll make a part 2 for the scientific notation section. So first, we said any number that's significant to the estimation is significant. Now, because of the nature of this problem, every single number here is significant, so we can just count our values. In our first one, we have 65.00, that's 4 significant figures, all significant to the estimation. 1.66, that's 3 significant figures, all significant. 3.2 centimeters, that's 2 significant figures. Notice I'm writing SF, significant figure. Also, sometimes we call them sig figs. So if you hear me call them or write SF, that's what I'm referring to. 37 seconds, that's 2 significant figures. Notice the 0 here is not significant, that's just a place value. So we have already dropped that when we wrote 37 seconds. 2 significant figures. 91.57 is 4 significant figures, and 48 milliliters is 2 significant figures.